I am Mr. Ish and I welcome all of you to this video. We're looking here at the synthesis of straight chain hydrocarbons like propane, butane, pentane, octane, all of that. And it's the most easy thing to do and the most enjoyable thing to do because we have a wonderful compound which is acetylene, which helps in the development of those hydrocarbons. It's an alkyne. It has a triple bond, HCCH triple bond here. Why is this a most feasible compound we can use for developing straight chain hydrocarbons? Because of these hydrogens, they are acidic. The reason why they are acidic is not mentioned in this video, but I have a video in which I am going to talk about it. The acidity of these terminal hydrogens makes them prone for synthesis so we can develop straight chain hydrocarbons. Just remember, these hydrogens are acidic. They can be plucked off with a strong base and a reaction can occur at the terminal ends. Let's look at all of this in this video. Acetylene is our parent molecule over here, and it's our most wonderful molecule for development of these hydrocarbons. And keep in mind, it's C2H2. That's what it is. We are starting here with acetylene, and then what we would do is attack it with a strong base. What is that base? It could be either lithium or sodium amide, NaNH2 or LiNH2, and it's sometimes pronounced as sodamide. As a shortcut, soda amide or sodamide. You can say it as that way. It's just an informal name, but we're looking here at sodium amide. It's a very strong base. It will pluck off one of these terminal hydrogens, and what will you have? You'll have an anion develop. It will be here an acetylide anion because it has a negative charge. It has a lone pair of electrons. It can act as a nucleophile for propagation reactions. We have acetylide anion. What will we react this with? Well, I'm going to react this with, let's just say CH3CH2Br. We have ethyl bromide. Where is ethyl bromide coming from? Ethanol, and you react it with an halide, you'll get ethyl bromide, and it will attack it over here and it'll expel that. What will be the result of this reaction? You have two carbons here and you're adding two more carbons. You're developing a 4-carbon chain. We will have here HC triple bond C and then CH2CH3. The hydrogen and the bromine, one hydrogen which is plucked off over here, and the bromine will become HBr, but I'm not showing that. But you see we've developed 1, 2, 3, 4 carbons. Now I can attack it again with another round of sodamide, sodium amide, and I can develop yet another anion, but on the other side, and this is what I have. I have this. What I will do here is now attack it with, let's say, CH3CH2CH2Br, propyl bromide. Now I'm adding 3 carbons, but on the other end, and we'll again have this negative charge attack over here, and the bromine will get pushed off. And what will we have? We'll have CH3CH2CH2, and now we have our acetylene functionality right here, the alkyne functionality, and then CH2CH3. What have we developed over here? We have developed a hydrocarbon, but it's a hydrocarbon with an alkyne functionality. You have 1, 2, 3, 4, 5, 6, 7 carbons, and you're numbering it so the carbon bearing the triple bond will have the lowest number. It'll be here. If you start from here, it'll be number 4, but this is what we have. We have 3 heptine. The YNE symbolizes an alkyne functionality, triple bond. But what can we do with this? We can start reducing it and get rid of that triple bond. And the reduction is easy. We have 3 heptine. We can reduce this and start bringing in an alkene or even an alkane. If you look over here on the top, I'll show you something interesting. Then we'll continue with that reaction. If you have an alkyne, let's just say this, and you react it with H2PT, this is catalytic hydrogenation, platinum catalyst. It will reduce this all the way to a alkane. You'll get rid of all the unsaturation and make it entirely saturated. A complete reduction all the way to a single bond. But however, if you did not use platinum and you use palladium, and this attenuated catalyst is called the Lindelar catalyst, where you're doing palladium instead of platinum, then you won't reduce it all the way down to a single bond. You'll take it down 1 step, 1 degree to an alkene. You will have this. That way you can do stepwise hydrogenation using Lindelar palladium catalyst. If you use platinum, it takes it all the way down to an alkane. You can react this now with another round of this catalyst and take it to the alkane. So you have the flexibility. You can either use platinum to go all the way, or you can use palladium to go stepwise, and that's what we can do over here. What I want to do is convert this 7 heptine, and I'm going to hit this right here with H2PD, Lindelar catalyst. And what will I have? I'll have an alkene develop, CH3 CH2, CH2, CH double bond, CH, CH2, CH3. What do I have? 1, 2, 3, 4, 5, 6, 7. And here's my third. I have here now 3 heptene. If I react this with another round of Lindlar catalyst H2 palladium, I'll develop heptane. From this step right here, if I just attacked it with hydrogen H2 but platinum, it would have gone all the way down to a heptane. It would have reduced even the double bond to a single bond. So these are the flexibilities you have. You can either develop using acetylene over here and this base and these alkyl halides, symmetrical molecules or asymmetrical. Here we have asymmetrical because I have 2 carbons on one end but I added 3 on the other end, so it's asymmetrical with regards to the functionality. I have uneven number of carbons on either end. So this right here is a good synthesis, all of it depending on acetylene, the acidity of its terminal hydrogens and a strong base and an alkyl halide, and obviously hydrogenation using either palladium or platinum to go down to a alkene or an alkane. Let's close this video out with one last example. We are starting here with acetylene, and it can also be called ethyne, E-T-H-Y-N-E, ethyne. The Y-N-E means triple bond and alkyne functionality is present. That's what we have, ethyne or acetylene. Acetylene is the common name. We will attack this with NaNH2 and we will have CH3Br, methyl bromide, and you know what you will have? This develop, because I've added 1 carbon to the terminal. The terminal hydrogen was removed by the base and then this came into play and we have this. What do we have over here? We have 1, 2, 3 carbons, but the numbering is 1, 2, 3. I have over here 1 propyne. That's what I have, 1 propyne. What will we do with this? Let's show you something. What I'm going to do is attack this with, again, sodium amide, but I'm going to react this with HC triple bond CBr. You see what I have gone over here? I have here acetylyl bromide, or you can say acetylid bromide. It's going to attack this terminal hydrogen. It's acidic. These hydrogens are not very acidic, and you will have, I'm going to draw everything as I see it. And this will add on this side. I'll have a C and then C and H. Now we have this. We have 2 alkyne functionalities. We have 1, 2, 3, 4, 5 carbons. We will obviously number with the first carbon here because I want to have the functional group and the unsaturated group on the carbon with the lowest number, and this is what it will be. How would we name this? We have over here 1, 3, and then we have pentane, but we have pentadiene. That's how we'll call it. There are 2 alkyne functionalities, hence the D over here. 1 and 3. The carbons 1 and 3 have the 2 triple bond functionalities. That's what they have. Pentadiene. But let's do something with this. If I were to hit this with the H2PT, it will get rid of everything which is unsaturated, make it saturated. All of these double bonds will reduce and we'll end up with CH3, CH2, 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 CH3. It would be pentane, but I don't want to do that. I want to attack this with Lindlar catalyst, where I'm looking at palladium which is weakened, it's attenuated. It will get rid of the triple bond. We will have this. Terminal carbon will be CH2, then we'll have a double bond, CH, single bond, CH, double bond, CH, and then CH3. And the valence should be good. We have 4 over here. We have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We're good. How do we number this? It will be here 1, 2, 3, 4, 5. And we'll name this as 1, 3, penta, and then diene. That's what it is. Pentadiene. 2 ene functionalities, meaning 2 double bonds, positions 1 and 3, and it's a pentane representation, 1,3 pentadiene. So you can see the flexibility we have and the awesome ability of this acetylene to help us develop straight chain hydrocarbons. You can even add on the terminal ends of this cyclic compounds, but we're keeping everything here straight chain hydrocarbons. And that right here is the end. Thank you for watching.